Kia ora, I'm Eliza, and I am part of the Capability Builder project, part of the project team there. Thank you for joining us for another NZARM webinar as part of the Capability Builder. Before we kick off, I would like to start with a karakia, and then I will introduce Brenda. E te hui, whai te mataranga Māori, te marama, ke whai tā ki ngā mahi katoa, tumaya, tukaha, aroha atu, aroha mai, tātou e tātou katoa. Welcome and thank you again for joining us on this webinar on landslides. I'd like to take a quick minute to introduce Brenda and then I'll hand over. Brenda has been working at GNS and is a geomorphologist with over 29 years experience across erosion and sedimentation. Brenda has recently worked on landslide hazards and risk assessments at GNS and has been heavily involved in the response to Cyclone Gabrielle and the storms up in the Marlborough Sounds, mapping landslides triggered by these extreme storm events. Before we start, can we please place any questions into the Q&A box at the bottom of your screen? We'll address these at the end of the webinar. Thank you. I'll hand over to you now, Brenda.
Kia ora. Right, I'll just share my screen. So that's all good there, Eliza?
Nope, I can't see that.
Oh no. Right, can you see that now?
Yep, just not in presenter view, but yep, there we go.
Right. Okay, kia ora everybody. So I'm Brenda. I'm a geomorphologist. I'm in the engineering geology team at GNS Science. I've been at GNS for about 10 years, working on landslides, mostly landslides, and I also worked for about 20 years at Manaki Whenua Land Care Research before that. I've also done a little bit of time over in California. Right, so today we're going to be talking about landslides, so basics of landslides. So this is an outline of what I'm going to cover. So, and firstly go over some of the landslide hazards in New Zealand, what exactly is a landslide classification and movement types, causes and triggers, where do they occur, so landslide susceptibility, some of the impacts, and I'll just quickly go over a rainfall-induced landslide forecast tool that we're developing at GNS. Okay, so landslides are actually the most common natural hazard in New Zealand, and they're the one that the natural hazard that most often affects property and infrastructure. They cost the economy at least $250 to $300 million a year. That estimate was done in 2016. So I think we all realise that those costs have gone up massively since then. An example is the Kaikoura earthquake in 2016, cost about $1.2 billion to rebuild State Highway 1 through Kaikoura there. And then Cyclone Gabrielle, it's estimated to have cost the economy about $8.4 billion, but that's including the flooding and the landslides. On average, there's about 2 to 3 deaths per year by landslides, which is actually more than earthquakes, which is pretty interesting. So what is a landslide? So in the most basic terms, a landslide is the movement of a massive rock or debris or earth down a slope. And the landslide is a term that sort of covers all those processes. So it's not necessarily restricted to land. It could be under the sea. And it includes all different types of landslides too. So falls and topples, slides. But we just use landslides to sort of include all of those sort of different processes. But when we're talking about landslides, we don't talk about ground subsidence, so the sinking of the ground, or glacier collapses, ice falls, or snow avalanches, or things like that. So what is a landslide? So landslides occur when the destabilizing forces or the shear stresses from slope steepness, weight, and groundwater, etc., exceed the resisting forces or the shear strength of the rock and the soil materials. So the shear strength is a term that's used to describe the inherent properties of the rock, to describe the magnitude of the shear stress that a soil can sustain. And it's determined by the steepness of the slope, the type of rock and its stability, the type of soil, and how the water infiltrates through that soil. So the stresses imposed on the slope can be sudden, like an earthquake, or from heavy rain, increasing the pore water pressure, or gradual, for example, like weathering, causing stress to build up on a slope over time. And the accumulation of damage can build up over time and gradually reduce that strength of a slope, eventually causing it to fail. So this is just some of the landslide features that you might see in the field. So the main ones that we are interested in are the source area. So that's where the landslide material originated from, where it came from. And the debris trails, so that is the deposit. And quite often there's not all of that material is evacuated from the source area, so we quite often get a bit of material that's still left behind. So we've got the landslide, the surf ruptures, or the sliding plane, and the head scarp up at the top of the hill there. And quite often you might find tension cracks around the top of the scarp, which indicate that the landslide might retrogress or move further up the slope. And then there's other sort of things that might indicate that there's movement, like such as ponds or ridges on the landslide deposit and seepage and stuff like that. So we can represent that in terms of the terminology here. So when we're mapping landslides and sort of trying to represent them in like a basic form. So this is how we look at it. So we've got the crown, the source area, so the displaced material, and that travels down slope, and the deposit or the landslide debris. So that's the run out area. And we're also interested in where that debris goes. So what does it impact or hit when it goes down the slope? So landslides are usually classified on their movement type, which is often controlled by the underlying rock type. So these are the main movement types that we deal with. So we've got slides, rotational and translational slides, falls, topples, flows, and avalanches, and spreads, lateral spreads that we saw like in the Christchurch earthquake. So then we can further subdivide that classification based on the materials that they form in. So we generally are dealing with engineering definitions of materials, so basically just rock or soil. So then we can subdivide these soils into coarse and fine. So the coarse materials being debris and the fine materials being classified as earth. Yeah, so these are the main ones that we deal with in New Zealand. So falls are basically just masses of rock or debris that move fall off the slope rapidly, generally off really steep slopes, and they free fall or bound down the slope. So slides are when you have a massive rock or debris that slides down a plane of weakness. So you can have rotational, where the sliding plane is curved, or translational, where the sliding plane is just flat. And these are often referred to as sort of like non-specific terms, as well as slips, landslips, or slippage. Avalanches, so you've got rock and debris avalanches. So these are typically really big, much larger landslides on very steep slopes. We often think of them as occurring in the like in the Southern Alps, within the Greywackies. So they might often start off as a rock fall or a slide and then transform into an avalanche as it moves down the slope and speeds up. And then we have debris flows and floods. So debris flows are type of landslide with really high sediment concentration. So they might often start off on the slope as a slide or an avalanche, and then if a lot of landslides are triggered at the same time and they all hit the stream system at the same time, or that material goes into the stream, they can sort of coalesce and form debris flows that move downstream as like a single flow and bulk up material as they move downstream. And then so the debris flows have a pretty, like the concentration of sediment is very high to the amount of water, and as it goes downstream they often transition into a debris flood where there is more water, so the ratio of water to sediment changes and there becomes more water downstream. So we can also landslides have a wide range in velocity of their movement types. So it can range from a couple of millimeters per year, like on an earth flow, or right up to a couple of like 200 kilometers an hour for debris avalanches or debris flows. So the velocity, so the movement rate of the landslides can also change through time, so they can speed up and slow down depending on environmental factors like groundwater level and rainfall, things like that. And landslides also vary extremely widely in terms of their size. So they can range from less than 10 cubic meters, like examples are the small shallow soil slips and flows that we've seen in farmland and stuff from Cyclone Gabrielle, right up to giant landslides, sort of 100 million cubic meters of material. And an example of that was one of the rock avalanches in the Kaikoura earthquake, which was the Hapuku landslide, which was about 20 million cubic meters of material. And I'll show you pictures of that soon. So we can also classify landslides on their activity, or the timing of how often they move. And this also has implications on their hazard potential, so what sort of damage they could cause. So active landslides are those of the landslides that are sort of moving within the last year or two, and inactive landslides haven't moved for a couple of years. So these ones could be either dormant, but there's still the potential for them for landslides to move, or they could be stabilized where there's been some remedial measures to try and stop the movement, or relict where they developed under different geomorphological climatic conditions that we're in now. So we can see them in the landscape, but they might be thousands of years old and they haven't moved for a very long time. An inactive landslide that starts to move again is called a reactivated landslide. And this is an example of a reactivated relic landslide from, this is Forsyth Island in the Marlborough Sounds. So on the left-hand side is a satellite image taken after the August 2022 storm event in the Marlborough Sounds. And the right-hand side is the LiDAR, which is pre-event. So I've outlined here in purple is the outline of a relic landslide that I could see in the pre-event LiDAR. And the pink are the landslides that occurred during the, which were obvious landslides that occurred during the August 2022 event. And it wasn't until I was drawing around the outside of this that I realized that the deposit was sticking out about 50 meters into the sea, compared to the coastline where it was pre the storm event. So this this whole bottom part of this ancient landslide, which might not have moved for several thousand years, has moved out into the sea here, and it's about 50 meters. Oh, so the green there are the debris deposits from the recent landslides. And we're actually starting to see this happen a lot more with these more intense storm events that are coming through. So we're seeing a lot of this happen in the Marlborough Sounds and as well as Gisborne. So landslide causes. So any factor or collection of factors that contribute to a reduction in slope stability is a landslide cause. So anything that changes the stress state of a slope. So these can include natural processes such as erosion, so rivers cutting down, cutting the toe off an existing landslide, waves and that sort of action, or weathering, so just gradual sort of weathering and forming of regolith on the landscape. So geological, which could include weak materials and defects within the rocks themselves. Human activities, so slope modification, things like putting in cuts and fills for roads, drainage, groundwater changes, and changing the vegetation on a slope. So other things that may cause landslides include things like snowmelt, springs, seeps, tree roots, wind action on trees, volcanic eruptions, mining, and rapid drawdown of water and things like that. So this is just an example of some slope modification and how that could cause landslide in the future. So this is an example of cuts and fills put in for road construction. So the cuts can both oversteepen this part of the slope, causing a stress change there, and also overload this slope here when the material is cast on the side to build the road. So this part is overloaded, which could also then fail into the river, especially if the river is cutting down and removing material from the bottom part of the slope as well. So these are sort of processes that precondition or set up conditions on the slope that may cause a landslide in the future. So then we have landslide triggers. So if any of the causal factors rapidly change the state of the slope and the slope becomes unstable, it's considered a trigger. So the main triggers that we deal with in New Zealand are rainfall, so storms, earthquakes, and then we also have landslides that occur with no obvious trigger, which we call spontaneously triggered landslides. So rainfall-induced landslides are the most frequent landslides that we get in New Zealand. So they're triggered by prolonged or intense rainfall. They tend to be small, but there tends to be a lot of them. And so these are triggered by rainfall, by storm events, approximately every 2 to 3 years. But I think we can all agree that with climate change, these are increasing. So rainfall triggered landsliding events are increasing in magnitude and frequency with climate change. So earthquake-induced landslides, they are triggered by earthquake shaking. So generally we consider it should be triggered by earthquakes of magnitude 5 or larger. And once we get up to a magnitude 7 or 8 earthquake, we're expecting those bigger deep-seated landslides that are pretty damaging. So generally landslides triggered by earthquakes are larger and they can cause more damage than the rainfall-induced landslides. And we expect a significant earthquake-induced landsliding event about once every 10 years. And so the example on the right-hand side there is the Hapuku rock avalanche, which was the 20 million cubic meter landslide on the Hapuku River. And it traveled 2.3 kilometers from the source area up here down the valley and blocked the river. Yeah, so it's massive landslide. So spontaneous failures can occur due to like gradual undercutting of slopes by erosion or rivers, weathering, weakening the rocks and the soils, and also man's activities can make that worse. And this is just an example of the Mount Adams rock avalanche, was about 10 million cubic meters, dammed the Puriora River in Westland in 1999. Yeah, and this landslide actually caused a magnitude 3.2 earthquake. So we could measure that in the GNS earthquake monitoring system. Yeah, so rainfall-induced landslides are the most common type of mass movement erosion that we have in New Zealand. So they're predominantly small and shallow. So they're normally earth or debris slides and flows. Although they're individually small, cumulatively they can cause a huge amount of damage. Like Cyclone Gabrielle has just recently been estimated to cost about 8.4 billion. And the most susceptible rock types are the young, so quaternary and tertiary rocks, poorly consolidated fine-grained sedimentary rocks, or the highly weathered, fractured, older, harder rocks such as the greybackies. And land cover plays a really important role in determining landslide susceptibility for rainfall-induced landslides. So landslide susceptibility really is what factors are controlling where the landslides occur in the landscape. So the main geophysical factors that control where landslides occur are the geology or the lithology of the rocks in the area that make up the slopes are made of. So the things that can affect the geology, the stability of the geology are the hardness, whether it's cemented, the age, the weathering depth, planes of weakness, and deformities such as faults, bedding, and structures within the rock mass. And slope, so that's including the slope angle, so how steep the slope is, and the aspect, which way that slope is facing, and also the slope curvature, the elevation, and the vegetation or the land cover. So how do we determine that susceptibility? Well, the most common way to do that is to map landslides triggered by specific rainfall events. Specific landslide events. So to do that, we normally produce an inventory. So we do this using aerial photography or satellite imagery obtained before and after the event. So we can do that either with storms or from earthquakes. So we really need to isolate the event so that we can relate the landslides that were triggered by that event to the magnitude of that triggering event. So that would be the rainfall amount or the earthquake shaking for earthquake-induced landslides. So this is just an example of rural Gisborne. So this is showing the imagery before, and this is after Cyclone Gabrielle. So we're in the process of mapping these landslides. This is just an example of one of the mapping methodologies we use. So that's the landslides. We've got the points located at the source of each of the landslides, and then we have lines representing the debris, the run out. And yeah, so we can use that in our modeling. but I'm going to be covering this more in the masterclass at the conference down in Christchurch in November. So if you're interested in more detail about landslide mapping, come to the masterclass. But so this is how we obtain our data or information about landslides, and we can start building models with all that data. So just wanted to give you a quick example. So this is the two storms that hit the Marlborough Sounds in July 2021 and August 2022. So you can see the rainfall that triggered that. So this is the rain radar from Met Service, and the black dots are the mapped landslides. So we map those landslides using satellite imagery. So we can then, so for each of those landslides, we know the rainfall that triggered it, as well as the soil moisture conditions at the time. So how wet the soils were at the time. We use the VCS and virtual climate station data from NIWA. And so from the mapping, we also know the exact location of the landslide sources. So we can overlay those sources onto the geophysical and topographic factors that are known to control landslide susceptibility. So for the Marlborough storm, we overlaid that onto the geology, which is on the left-hand side, and the land cover type on the right-hand side. We also looked at slope as well. So that allows us to analyze what factors are controlling where the landslides occurred. So this is just an example of some of the, this is one way we can look at the statistics from where to get an idea of what's controlling where the landslides are occurring and developing relationships between landslide occurrence and the susceptibility factors. So what we're looking at here is, so we've got rainfall, slope class, the rock type, and the land use. So the open bars represent the proportion of the study area that is occupied by the land class of that type. So this is about 5% of the study area is represented by slopes of 10 to 20 degrees. And the dark bars are the percentage of landslides that occurred within that area. And actually, the black line is the landslide density, so how many landslides occurred per kilometre. But what this shows us is that the landslides didn't occur evenly across the whole study area. So what it's showing us here is that the landslides preferentially occurred on slopes from 20, 30 and 40 degrees slope. So they preferentially occurred on those slopes because they occurred more often than those slopes are represented in the study area. So that's for slope, but with rainfall, you can see here that the most landslides did not necessarily occur where the highest rainfall was. And so that means that there's other factors controlling where those landslides were occurring. And these other graphs are sort of giving us information about what other things might be controlling that. So one of them is definitely slope. And you can see here with the rock types, so the landslides preferentially occurred on the Waipapa terrain and the Pleistocene Holocene sediments. And for land use classes, we can see that landslides preferentially occurred on pasture and scrub slopes. So they were sort of overrepresented compared to the area that they occupied within the study area. But then on the other hand, we can see that Indigenous forest was really underrepresented. So that Indigenous forest made up about 50% of the study area, land area, but only about 5% of the landslides occurred on the Indigenous forest. So that gives us a clue that the vegetation or the land use class has got some sort of control of where those landslides are occurring as well. I just wanted to say a quick thing about landslide susceptibility, hazard, and risk, because I know that sort of these terms get thrown around and used a little bit, sometimes not quite in the correct way. Oh, sorry about that. So landslide susceptibility is the likelihood of a landslide occurring in an area based on the local terrain conditions, and it predicts where the landslides are likely to occur. It doesn't take anything else into account. It doesn't take into account what rainfall might trigger those landslides or how big they might be. So that's just the susceptibility. So landslide hazard combines the susceptibility with the estimates of the likelihood of a triggering event. So how often are those rainfall events likely to occur? So that's when we're looking at rainfall return periods from NIWA, and also takes into account estimates of the magnitude and frequency. So how big are those landslides likely to be, and what sort of, how far down the slope could they move? And then risk. So landslide risk maps combine the probability that a landslide will occur from the hazard map with an analysis of all the possible consequences. And so what are the impacts of those landslides? And that takes, so that's sort of considering things like property damage, how much is it going to cost to repair that property, casualties, loss of life, loss of service. So for example, like if Manawatu Gorge being closed by landslides, how much does it cost for those trucks to go a lot further around to get to the other side of the Manawatu Gorge? So just a little bit on the impacts of landslides. So we've got on-site impacts, so like the direct impacts, including deaths and injuries. We've got road closures. We can have damage to farm and forestry infrastructure, like losing the fences, damage to utility networks, electricity, gas, water, etc. An example of that is the Gisborne water supply pipeline was damaged in about 7 places, and several of those areas where the pipeline was damaged during Cyclone Gabrielle was caused by landslides. Another impact is the loss of productive topsoil. So when you get a landslide, it removes the original soils that were produced under the forest, and when a new soil is forming in that eroded land, it takes a long time for it to build up those nutrients and the soil properties that the original soils had. So there's a long-term loss of productivity from those areas where the original topsoil has been lost. So off-site impacts from sediment delivery and deposition in rivers and streams. So that includes things like water quality degradation, habitat degradation from aggradation, sediment buildup in rivers, which causes river instability, increase flooding risk, bank erosion, and things like that. And also water supply disruptions due to the sediment being delivered to the river systems and causing the high sediment loads. So some of the impacts to the built environment. This is just some examples from recent storm events in the last 2 years. So this is Wellington, this is up in Piha, and Marlborough Sounds. Yeah, so the damage from landslides to houses can be can range from nothing much to complete destruction and removal of a house. Sorry, I was going to say this house here had the whole top floor removed by a landslide, and the roof then came down and collapsed. So at the moment, we're doing some research to try and link the size and type of the landslide to the damage that they cause, and so that we can sort of estimate damage costs and impacts from that. One of the other big impacts from landslides are landslide dams. After the Kaikoura earthquake, the landslide dams were actually considered the greatest hazard following the earthquake because there was the possibility of if there's a landslide dam that forms during an earthquake or a storm event and it's up in the top of a catchment and nobody knows about it, and that landslide dam fails rapidly, and then all that water is released simultaneously, they can cause devastating floods downstream, and that's one of the greatest hazards following an earthquake or storm event. This is just some examples of the landslide dams caused by the Kaikoura earthquake. This is the Hapuku that we looked at before. And this is the Mangahawini landslide dam, which was triggered by Cyclone Gabrielle, just 3 kilometers upstream from Tokomaru Bay. So you can see the landslide, which was actually a relic landslide that was reactivated, traveled down the slope here, blocked the Mangahawini River. This is State Highway 35. So buried State Highway 35, and there was a lake upstream of the dam here. And this is looking upstream. The landslide came from up here around the corner, buried the road, and the lake was up here. So we were asked by Gisborne District Council and NEMA to do some modelling. If the landslide dam collapsed simultaneously and released all the water that was in the lake, what the downstream flood levels would be like. So we provided that information to Gisborne District Council, who then made the decision to evacuate Tokomaru Bay Township, which was down here, which luckily it didn't, but if all that water and material had gone all at once, then there could have been some severe flooding in Tokomaru Bay. And lastly, I just wanted to go over a rainfall-induced landslide forecast tool that we're developing at GNS. So we're developing the tool in Wellington. We've developed in Wellington, and we are now applying it to the rest of New Zealand. So we had a database of about 17,000 landslides in Wellington. So we knew the date and the location of all of those landslides, but there was 11 storm events where we knew the exact rainfall that triggered them and the soil moisture conditions, as I said before. So we are developing, for all those landslides, we've overlaid them onto the landslide susceptibility factors, and we've done some modeling using logistic regression analysis and AI, machine learning. And we started off with looking at about 13 different landslide susceptibility factors, so things that could be controlling where the landslides are occurring. And we narrowed that down to 8. So the inputs into the model, so for each of those landslides, we have data for all of these things, which we can do. Then we can do the analysis. So in the model, we've got rainfall. So that can be static. So it could be like a return period, like a 100-year event from NIWA, or it could be an actual storm, the rainfall that fell in an actual storm event, or we could have that as dynamic, so it could change. So we can have the rain gauge information or rain radar coming in as sort of as our trigger layer, and we also have the soil moisture. So the landslide susceptibility factors that came out as being the most important controlling where these landslides were occurring in Wellington ended up being the elevation, the slope aspect, local slope relief, which is basically just the height of the height difference between the top of the hills and the valley bottom, the geology, and the land cover. So then we can use that model to predict the probability of where landslides are, the probability of a landslide occurring on a given slope with a given rainfall. So the outputs of the model, in Wellington, we've done it on a 3-meter pixel, but for the rest of New Zealand, we're working on a 32-meter pixel. So on the left-hand side is the output for a 100-year return period event, which is about 150 millimeters in 24 hours for Wellington. And on the right is a 200-year event. Yeah, so you can see the areas of red are the areas with the highest probability of landslide occurring. And you can see as we increase the rainfall, or the return period, there's a greater area of that covered in the higher probability of a landslide occurring. So this is just an example. We ran the tool for the August 2022 atmospheric river event. So this is on the left is the outputs from the tool, so the showing the areas of high probability of landslide occurrence, and then compared to the actual landslides that occurred during that event. Lastly, I just wanted to show you how we use the tool in Cyclone Gabrielle. We had weather forecasts coming in from NIWA, so we were updating the forecast every 6 hours. We were running the tool to produce the running the rainfall-induced landslide forecast model. We normally run the tool off actual rainfall data, but because during Cyclone Gabrielle there was no information coming out of East Cape or Hawke's Bay because the communication was down, so we had no internet, and so we're getting no rainfall information. So we decided to go for the forecast instead of the actual rainfall. So yeah, so we were supplying these the model to all the stakeholders around the North Island who were interested in impacts of landslides in their regions. So we had the outputs from the forecast tool, which we then ran through RiskScape, and we could get indications of the numbers of homes that would be impacted by landslides, the number of landslides per kilometre of road, and the number of landslides per kilometre of rail. So we're getting into that risk forecasting and being able to look at where those impacts are going to be from the landslides during Cyclone Gabrielle. So that was the first time we've ever done that, and it actually worked out really well. Well, the modelling worked out really well. Sorry. Okay, so in summary, landslides are common and widespread throughout New Zealand. They occur in a variety of types, in all different sizes, and they move from very slowly right through to very rapidly. Rainfall is the most common trigger of landslides, but large earthquakes are known to trigger much larger landslides. And landslides have already had a considerable impact on New Zealand society and will present a significant risk in the future, especially with the increasing magnitude and frequency of the intense storm events that we're starting to see. Yeah, so that's it from me. Hopefully there's time for some questions.
Awesome, thanks, Brenda. We've got a couple of questions that have come in. So the first one here is there a good understanding across the range of geological landscapes of the relative proportional contribution of landslide mass versus USLE type surface erosion?
We do have a pretty good yeah, I'm not sure how it compares to the American methodologies, but we do have pretty good understanding of the different rock types and how they behave, and also how those different rock types deliver different amounts of sediment to river systems. So sort of we're developing those relationships with the development of our forecast tool, but also there's a whole lot of information that's been around for a long time in the NZLRI, and so Landcare's modelling can looks at enzymes. So they've got different erosion rates for different rock types. Yeah, so I think we do have a pretty good handle of that in New Zealand, but yeah, I'm sorry, I can't comment on how it compares to what they do in America.
Awesome. And we've just got another one here mentioning that you use both landslide and slope as factors that affect landslides, but there's a point making that forestry would be on steeper slopes. So could there be the potential to combine the two factors together, the slope and land use, to then arrive at the susceptibility?
Can you repeat that again? Sorry, Eliza.
Yeah, so it's just pretty much asking regarding forestry, and so you looked at the land use and slope as factors that affect landslides.
Yeah.
Is there the potential to combine those two?
We kind of they're independent factors. I mean, I understand that forestry is used as a protection method to, on the steeper slopes and on the more highly erodible slopes, but I don't. We need to treat them separately because they are, they're independent factors that have different controls over where landslides occur. But with the tools that we are developing, and also with the tools that Landcare have developed, we can change the land use and look at different what would happen. So look at different scenarios if it was say pasture compared to forestry, and take the landsliding into account that way. But yeah, I think that you would need to treat those two things separately because they are different. They do have different controls on where landslides occur.
Awesome. And one of the slides, I think there was one we had the 4 graphs there. It was scrub. There, people are wondering what scrub was defined as. Is that Manuka and Kanuka?
Yeah. So we use the land cover database, and we just combined a whole lot of the categories to call it scrub. So it's Manuka, Kanuka, fernland, Mataguri, and a whole lot of vegetation types that sort of just represent forest, so regeneration, I suppose. So early stages of forest regeneration after it's been cleared. So the sort of those areas represent areas that have been farmed in the past and are now regenerating back into native forest.
Awesome. We've just got one last question here. It's more of a statement, but regarding the landslides in Hawke's Bay and around the east coast, it's noted that it might take over 100 years to restore that topsoil status.
Yeah, I know. Yeah, I did that research. Well, actually, I carried on the research of Noel Trustram and Lambert et al. Co. So, yeah, it may not ever get back to the levels of nutrients in the soil structure that was before in the original forest soils.
Cool. We'll have a couple of more have come in. So has forest erodibility been mapped from an age class perspective for some of these recent events?
No, not that I know of. At the moment, we're in the process of mapping all the landslides. And unfortunately, forest age class is one of those information layers that is not really readily available. Yeah, I'm not a forester, but my experience is that it's hard to get the information from. I don't know if, you guys could probably tell me, being involved in regional councils, whether that information is available. I know that there's definitely some plans to look at forest age, which can be done with LiDAR and things like that. But yeah, that's something that we're looking into. We're definitely, so the moment we're mapping the landslides, we're definitely going to be looking at the land use and the past land use where all those landslides occurred, and possibly probably updating our models with that information.
Awesome, thank you. We'll just leave it there. That seems to be all of the questions. But thanks again, Brenda, for your time today. And this webinar recording should hopefully be on the NZARM website shortly. And for those interested in Brenda's masterclass, a link will be sent out shortly for those who are wanting to register. Thank you. Have a good rest of your day.
Kia ora. Thanks, Eliza. Thanks, everyone.